All right, class. So now that we know how to make alcohols, we're going to look at reactions of alcohol. So what can you do with an alcohol? A couple things to remember. OH minus is a bad, so hydroxide's a bad leaving group, but water is a good one. So also keep in mind that alcohols are weak nucleophiles, but the alkoxide is a strong nucleophile. So those are just some things to keep in mind as we go through these reactions of alcohols. And just to keep in mind the ladder of oxidation. Um, the we went over in the last lecture we went over being able to go down the ladder, so reducing the carbonyl compounds to make alcohols. And what we're going to find now is that one of the reactions we can do is we can oxidize alcohols to corresponding carbonyl compounds if we have the necessary reagents. So we just went over going down the ladder. Keep in mind that what we're going to one of the reactions we're going to go over is oxidation of the alcohol to the corresponding carbonyl compounds. All right, so let's start with acid catalyzed dehydration. So this is something that we went over in chapter 7. So what we found in chapter 7 is that tertiary alcohols are readily dehydrated with acid. Secondary alcohols require a slightly higher temperature, and that primary alcohols are really hard to do to eliminate. This is an E1 elimination. So let's think about the mechanism by how this reaction works. All right. So I have an alcohol here. I have H3O plus. THF is the solvent. We're not going to worry about that. So we have this alcohol. We have the acid here. So we're going to treat this as H plus. So whenever you have H plus, the first step in almost every mechanism is a proton transfer. This is the nucleophilic atom. So we're going to do a proton transfer. That is going to, so remember, in an E1 elimination, the leaving group has to leave. OH minus is a bad leaving group, right? So that's not going to leave on its own. But if I turn the OH into, if I protonate the OH, that makes the oxonium, and now this is ready to leave. Now this leaves as water, which is a good leaving group. Water is a good leaving group. OH minus is a bad leaving group. When that leaves, that makes the carbocation there. That carbocation, a number of things could have it. We could have something attack it to do an SN1 reaction. Because this is a tertiary alcohol, and we don't really need to heat it all that much, we're going to do an elimination with the conjugate base of the acid. So the conjugate base of H3O plus is water. And remember, we're catalytic in acid, so we have to regenerate the acid anyways. So I'm going to remove this proton. I'm going to do a proton transfer. And I'm going to make the double bond here. And remember, you make the more substituted double bond because you're making the Markovnikov or the Zaitsev product. So this is the mechanism just drawn out on and how your book draws it out. So proton transfer, leaving group leave, elimination, proton transfer elimination to give you the Zaitsev product. And the reason why tertiary alcohols are, so one of the things to keep in mind is why is it harder to react secondary and primary alcohols? Well, the reason it's harder to react primary and secondary alcohols is due to the carbocation that you form in the intermediate. Because you're doing an E1 elimination, the more stable the carbocation you form, the faster the reaction. So because you have a tertiary alcohol, the carbocation you make is going to be a tertiary carbocation. If you had a secondary or primary alcohol, those carbocations are less stable. So that's why they're harder to react. So we can take alcohols, we can dehydrate them in an E1 elimination type of process. So like I said, we've got, the previous lecture we went down the ladder, we reduced carbonyl compounds to make alcohols, and now what we're going to go over is how we can take alcohols and oxidize them to the corresponding carbonyl compounds above them. We're going to go up the ladder. So what reagents can we do for oxidation? Well, if you kind of think about it, these are different types of there are a myriad of oxidizing reagents. And they kind of fall into one of two categories: strong oxidizing reagents or weak oxidizing reagents. Generally, when you have a metal with a bunch of oxygen attached to it, those are relatively strong oxidizing agents. So KMNO4, chromium trioxide, sodium dichromate, The commonality between all of these is that you have a metal with a bunch of oxygen. Manganese with 4 oxygens, chromium with 3 oxygens, 2 chromiums with 7 oxygens, a ton of oxygen. These are strong oxidants. And what these strong oxidants will do is they will basically make as many bonds to oxygen as possible. So for example, if you use a strong oxidant, the strong oxidant will take a primary alcohol, oxidize it to the aldehyde, but then this can be further oxidized to the carboxylic acid. So a strong oxidant will go from the primary alcohol all the way to the carboxylic acid. Basically what you're doing here, if you notice, is that when you're doing an oxidation, you're replacing any hydrogens of that carbon with bonds to oxygen. So if you already have one bond to oxygen, you can replace one of those hydrogens with another bond to oxygen to make the carbonyl. And then you can replace this other hydrogen, if you have a strong oxidizing agent, with another bond to oxygen in the form of OH. So these strong oxidants will take a primary alcohol all the way to the carboxylic acid. These strong oxidants will also take a secondary alcohol to the ketone. Notice that when you replace this hydrogen to make a bond here, there are no other hydrogens on this molecule to oxidize. So it stops at this is the most oxidized you can make a secondary alcohol. You can't oxidize a tertiary alcohol up to anything. Now, there are also what we call mild oxidizing reagents, and these oxidizing reagents can take the secondary alcohol to the ketone, and they will also take primary alcohols and stop them at the aldehyde. So we can stop in this middle here for primary alcohols if we use a weaker oxidizing reagent. So the one that the book goes over was known as Des-Martin periodinane. So this is a weak oxidizing reagent. So just to go over this, if I have a primary alcohol, this primary alcohol gets oxidized all the way to the carboxylic acid. It goes through the aldehyde, but you can't isolate the aldehyde in most cases. And then the secondary alcohol with these strong oxidizing reagents, they get oxidized to the ketone, as you see here. We can also take alcohols and we can convert them to ethers. So remember that this is a weak nucleophile. But if I could make this, if I could deprotonate this, then I could make the alkoxide, and that's relatively reactive. Now we know the pKa of alcohols is such that you either have to use a fairly strong base to deprotonate. You can't use hydroxide to deprotonate most alcohols. But one way you can make the alkoxide is reacting the alcohol with either sodium hydride, potassium metal, or sodium metal. Any of those 3 things will get rid of the proton here and make the alkoxide. Once you have the alkoxide, remember, if you have to look at this molecule and you think if it's nucleophilic or electrophilic, well, it's negatively charged, so it's probably a nucleophile. And because I have a nucleophile, if I can react that thing with electrophiles, I could make a bond between this and some electrophilic molecule. Well, this is a good nucleophile. If I take this good nucleophile and I react it with an alkyl halide, I could do an SN2 reaction to make a bond between this and another carbon. So what's going to happen here, once I make the alkoxide, I can take this alkoxide, so this is a strong nucleophile. This is going to react in an SN2 manner with primary alkyl halides and kick out the iodide. Now you can also do E2 elimination reactions depending upon the reaction conditions, okay? The more hindered the alkoxide, the more likely you're going to start doing the E2 elimination. The more you heat this step, the more likely you are to do the E2 elimination. So once you do that attack, so once you make the alkoxide, the O- attacks the methyl group in an SN2 reaction, kicking out the iodide to give you the ether. So in this case, cyclopentyl methyl ether. This is an SN2 reaction. This overall sequence of starting from the alcohol, making the alkoxide, and notice that when we make the alkoxide, right, like a lot of times the sodium is written, but it's just the counterion. We don't care about the counterion. We're really concerned about the O-. The O- attacks the methyl group, kicks out the iodine. So the next thing we're going to cover are reactions of phenols. And so just to kind of give you a heads up, phenols can do a lot of the same reactions of alcohols, like ether synthesis. They also do oxidations, but they look a little bit different. All right, so that's it for this lecture. Let me know if you have any questions, and I hope let me know if you have any questions, and I will talk to you later. Thanks.